Welcome back to The Explainer. So, if you're the kind of person who loves peeking behind the curtain to see how the universe actually ticks, you are absolutely in the right place. Today, we're taking a deep dive into the hidden, microscopic rules that completely dictate how our macroscopic world behaves. We're talking about the invisible machinery of matter itself. Let's get right into it.
Here's our roadmap for today. We'll start with 1. Meet the 3 states. Move into 2. Kinetic particle theory. Then 3. How matter changes state. 4. Temperature, pressure, and volume. And finally, wrap up with 5. The magic of diffusion.
All right, Section 1. Meet the 3 states, the macro world. Let's ground ourselves with something super familiar. Just imagine gorgeous, towering, snowy mountains. That is solid matter in all its glory. Now, solids are defined by having a definite volume and a definite shape. Sure, they might expand or contract just a tiny bit if the temperature shifts, but overall, they stubbornly hold their ground.
Now contrast that with the liquid state, like the water in a stunning, wide-open bay. Liquids are a bit more flexible. They hold on to a fixed volume, but they freely take the shape of whatever is containing them. They flow, but here's the catch. They're practically incompressible. Try squeezing a liter of water into a half-liter bottle. Yeah, no way. Not going to happen.
And finally, we've got gases, like the intense steam shooting out of a geyser. Gases are the ultimate rule breakers. They spread out evenly to fill literally any container you put them in. No definite shape, no definite volume. And unlike our stubborn liquids, gases are highly compressible and wildly sensitive to changes in temperature and pressure.
Moving right along to Section 2, Kinetic Particle Theory, the Invisible Rulebook.
So we're going to zoom all the way in now, past the mountains, past the oceans, down to the invisible secrets making them work. Enter kinetic particle theory. Think of this as the ultimate invisible rulebook of the universe. It basically says that all matter is made up of these tiny, invisible particles, and, here's the kicker, they never stop moving. The physical properties we see out here in the big macro world entirely dictated by how these microscopic particles are arranged and how fast they're moving. And temperature? Temperature is literally just the speed dial. Crank up the heat, and those particles move faster. Simple as that.
Okay, so the big takeaway here is that the difference between a hard block of ice, a cool glass of water, and invisible steam, it isn't what they're made of. They're all just H2O. The whole difference is just how those particles are organized and moving. In a solid, they're packed super tight, practically shoulder to shoulder, just vibrating in place. In a liquid, they've got enough energy to wiggle and slide past each other. And in a gas, they are far apart, zipping around completely freely at incredibly high speeds.
And this is where it gets really wild, seeing how the micro completely controls the macro. When you have particles packing tightly together in a strict, repeating geometric pattern, that microscopic architecture directly translates into the stunning, sharp geometric shapes of real crystals we can actually hold in our hands. It's literally microscopic architecture building our macroscopic world.
Which brings us to Section 3, How Matter Changes State, Energy, and Temperature.
Let's talk about the ultimate instigator here, energy. Changing states is all about energy. Imagine heating up a solid. You're pumping energy into that system. Those tightly packed particles we talked about, they start vibrating faster and faster until, bam, they're vibrating with so much energy they literally shove their neighbors away. The invisible forces holding them together get weaker, the rigid structure completely breaks down, and boom, it melts into a liquid. Add even more heat, and they break free entirely, boiling off into a gas. But get this, before they completely break free and melt, those faster vibrating particles push against each other and take up slightly more space. And this tiny, microscopic expansion, it has massive real-world stakes. Think about a railway track. If engineers didn't intentionally leave expansion gaps in the tracks, the hot summer sun would energize those metal particles, causing the massive steel rails to expand, bend, and completely buckle. That is microscopic motion causing macroscopic destruction.
Now here's a detail that totally catches people off guard. Say you're melting pure ice into water, right? If you track that with a thermometer, the temperature won't rise a single degree. It will sit stubbornly at 0 degrees Celsius until every last microscopic piece of ice has melted. Why? Because all that heat energy you're adding is going straight into breaking those bonds between the particles, not into raising the temperature. It's only after it's 100% liquid that the temperature starts to climb again. Pretty cool, right?
Moving on to Section 4, Temperature, Pressure, and Volume, How Gases Behave.
Let's look at how these hyperactive particles physically push against the stuff around them.
Have you ever left a balloon in a hot car and wondered why it swells up? It is simply a matter of collisions. Inside that hot balloon, the gas particles are jacked up on energy. They're moving super fast, violently smashing into the rubber walls over and over again. This increased internal pressure literally pushes the walls outward, puffing up the volume. Take that same balloon, make it cold. The particles get sluggish, the collisions get weak, and the whole thing shrinks right back down.
You can actually feel this physics happening in the palm of your hand. Think about using an old-school manual bicycle pump. As you shove gas molecules into the tiny space of a tire, you're cranking up the pressure. You're forcing those particles way closer together, making them slam into each other constantly. All that microscopic friction and colliding, it generates actual physical heat. That's why the metal barrel of a bike pump gets noticeably hot while you're pumping.
And that brings us to our final section, Section 5, the magic of diffusion, spreading outward.
Let's bring all these invisible mechanics right into your kitchen. Have you ever opened a fresh jar of coffee or peeled an orange, and almost instantly, someone all the way across the room says, "Oh, that smells amazing"? We've all been there. Well, kinetic particle theory tells us this isn't magic. It's just randomly moving gas molecules from that coffee, constantly bouncing and ricocheting through the empty spaces between the air molecules in your room, spreading out until they physically crash right into the scent receptors in your nose.
In this spreading out, or diffusion, happens in liquids too. But think back to our invisible rulebook. Liquid particles are packed closer together, and they aren't zooming around nearly as frantically as gas particles. Because it's such a crowded, slower-moving environment, diffusion in liquids takes way more time. This is exactly why dropping a little bit of food coloring into a totally still glass of water can take literal days to fully mix and turn the whole glass green.
But even among gases, there's actually a microscopic drag race going on. Physics dictates that the lighter particles are always going to win. Gases with a smaller relative molecular mass, like ammonia for example, are lighter, so they're going to travel and diffuse significantly faster across a room than a heavier gas like hydrogen chloride, assuming they're at the exact same temperature. It's purely a matter of mass.
Which perfectly tees up this fantastic quote from our source material. Chemistry is about what matter is like and how it behaves, and our explanations and predictions of its behavior. I mean, that hits the nail on the head for this explainer, doesn't it? By understanding these hidden rules, the vibrations, the collisions, the energy of these tiny invisible particles, we literally unlock the ability to predict, understand, and manipulate the massive visible world we interact with every single day.
So I'm going to leave you with this final kind of mind-bending thought. The desk in front of you, the floor you're standing on, even your own hands, everything is ultimately just a vast, vibrating swarm of tiny moving particles held together by invisible forces. When you really stop and look at it through the lens of this invisible machinery, how solid is the physical world you're standing on, really? I hope this explainer sparked a little curiosity in you to look closer at the everyday things around us. Keep wondering, keep learning, and we'll catch you in the next explainer.